this video, I am going to explain about AVL Trees, one of the efficient searching technique. Okay. Now, this AVL Trees, why the name is, what is that AVL? So, this AVL Trees are invented by two Russian scientists, person called G.M. Adelson Velsky and E.M. Landis. Okay, so they invented this AVL trees in 1962. Hence, they named the tree as this AVL. So, Adelson Velsky Landis tree. Okay, this is what AVL tree. So, this is just for information. So, now, before going into the AVL trees, now I will going to explain what you mean by binary trees, that many of you know, I think, binary tree, and what you mean by binary search trees. Okay, so binary search trees I'm using, and then what is the disadvantages of this binary search tree, and then how to overcome that. Okay, that are the things I'm going to cover. Then I'll come to the AVL trees and how this AVL tree will do that searching operations. Okay, so how to construct the AVL tree for the given set of elements, that I am going to explain with some examples. Suppose if you people are good in this binary trees or binary search tree, you can directly go for this AVL trees. So otherwise, just you watch from the beginning for these two binary trees and binary search trees. Okay, so now binary tree are the tree in which every node is having maximum of two childs. Okay, so in any node should not having more than two nodes. For example, see, this is one node, for example. Now this can have maximum two. This node cannot have a third one. This is a root node. Okay, now this is having one, so this is having two, this is having binary tree. Okay, so that means maximum any node can have only what? Two nodes. You can have zero nodes. See, these are called leaf nodes, which doesn't have any child nodes. So these are called the leaf node. This node is having two child, and this node is having only one child, and this is having only two child. So maximum any node can have only two child. That is what the binary tree. Now, binary search tree is just a variation of binary tree in which all the elements of the left subtree should be lesser than the root node or its parent node, and all the elements in the right subtree should be greater than its parent node or its root node. Okay, so that is the definition of what binary search tree. For example, now let us take, for example, say this is say 8, this is 8, and this node should be lesser than this one. Whatever you can take, say 5, say this is some 2. Okay, but this is a right subtree. This should have values more than this 8. Now this may be what, assume 10. This is 10, and now this always left child or left subtree should be lesser than its parent. Now it should be lesser than, but it should be greater than this one. So it should be 9 in this example. Okay, now it is whatever is more than greater than 10. Okay, let us say 50. So this is greater than. So now if you observe all these elements, this is what right subtree. All this is what right subtree. All the elements in the right subtree is greater than the root, and all the elements in the left subtree are lesser than the root. And this also, this left child should be lesser than this parent node, and this node should be lesser than this parent node. This node should be greater than its parent node. This is what binary search tree. Now, what is the advantage of arranging the elements in this fashion? If you arrange the element in this fashion, searching becomes very easy. How? For example, assume here I want to search, for example, say I want to search element 2. This is my key element. Key element I need to search was 2. Now what I will do, first I will search, which always will come from the root. See, key element is equal to root. No, it is not matched this one. Now I'll check whether the key element is lesser than the root element or greater than the root element. Key element is 2, it is lesser than the root element. So, no need to search here. I need to search only the left subtree because all the elements in the left subtree should be lesser than the root node. So, I have to search here. So, then I will come here. Now, again I will match. The key element 2 is equal to 5. No, again mismatch occurs. Now, again I will check. Whether I need to search in the left or right, since key element is lesser than the key element, this one, so I have to search in the left, so I come to left, so here I find. So I did what? 3 comparisons I did, okay? 1 comparison, 2 comparison, 3 comparisons. So that means I found the element after 3 comparisons. So only 3 comparisons. Now, what is the height of this tree? See, now instead of starting height 0, now I am starting the height from what? 1. Okay. So this is at 1, 2, this is 3. Now height of this tree is what? 3. Now let us take the same element. Same element. Now I will instead of these elements, now take the order like this element. Okay. For example, I say 15, then 10, 9, 8, 5, 2. See, same elements. I took this in this order. Now if I construct this one, the first element is 15. 15 now. Next element is what? 10. So 10. Where to insert? To the left or to the right? Okay, 2 options are left or right. Since 10 is what? Lesser than this one, I have to insert at what? Left only. I can't, because all the right subtree should be greater. Left subtree should be lesser. So this should be inserted at left. Next. This element over, this element over. Next, 9. Where to 9? 9. Okay, not greater, lesser than, come to the left. Again lesser than, come to the left. Now inserted here. Again, this element is over. Next, 8. Again to the left. Okay, this 8. Next, 5. Again lesser than this, lesser than this, lesser than this, lesser than this. So I inserted here. Now last 2. Lesser than this, lesser than this, lesser than this, lesser than this, lesser than this. So I inserted here. Suppose any element is greater, I have to come here. Suppose for example, here is 20. I have to insert 20 here. But in this example, we don't have that element. So I am not using this element. Okay. Now this is the tree. Again, this is also binary search tree. Binary tree. Binary tree means what? Every node should have maximum 2 nodes. Child, maximum 2 child. See, this is only 1 child. This is only 1 child. This is the grandchild. Again, this is only 1 child. This is only 1 child. This is only 1 child. So maximum 2 child. Yes, this is also my binary search tree. Now assume here I want to search. Again, my key element is equal to 2. Again, my key element is equal to 2. I have to search. Again, we need to start always from where? From the root node. From the root node. No, it doesn't matches. Since key element is lesser, have to come left side only. Left. Again, the mismatches, 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 mismatches. Now it matches. How many comparisons we did? 1, 2, 3, 4, 5, 6. 6 comparisons I did. So number of comparisons is equal to what? 6. Now, what is the height of the tree? See, if you see, height of the tree is, this is, I'm starting from 1. Actually, generally most of the people will start from 0, then you have to add 1 at the end. Instead of that, I'm starting from 1. Okay, so now here the height, level 2, 3, 4, 5, 6. Now, height of this tree is equal to what? 6. Height is equal to 6. Now, what is the thing? See, here height of the tree is 3 in this case, and we need 3 comparisons we took in order to find the key element. Again, the same elements we took, same elements, but in this case, height of the tree is 6. Height of the tree is 6. Number of comparisons up to 6. That means at the best case, no, this is best case. That means I found the element at the 3rd comparison only. So at the best case, I am having only 3. So that means log n. That means log n. How many? N is number of nodes. So log n time. Okay, but here this is the worst case. Maximum number of comparisons. At the last leaf node I am finding. So worst case means big O I am finding at n. That means if that means the number of comparisons or time taken by our searching in the binary search tree, it depends upon height of the tree. Height of the tree. So I can say height of the tree is equal to what? Number of comparisons we need here to find. In most of the cases, if the tree is not balanced. Now, here the thing is, since the height of the tree is more, here height of the tree is very less, so number of comparisons is less. So how much the height of the tree is more, that means more number of comparisons we need to do. So this is the major disadvantage of what? Binary search tree. So to overcome this disadvantage of binary search tree, we go for what? AVL trees. Now what this AVL tree will do, this AVL tree will reduce the size of the height of the tree. That's it. It reduces the height. And another word I can say, why the height becomes more, the word in which case your height is more only towards the left subtree. I don't have right subtree. So that means the tree is not balanced. That means in both left and both are not balanced. But here you see, both are balanced. Height of the left subtree is what? Only one. See here also one. Only the height is balanced in both left and right. But here left side is more weight. There is no nodes on the right subtree. That means the right and left subtree are not balanced. So in order to balance the binary search tree, okay, in order to balance the binary search tree, we go for this AVL trees. So hope now you people understood clearly why we go for AVL trees. Okay, so we go for AVL trees, or AVL trees are used to reduce the height of the tree, or the same thing I can put it in another word, in order to balance the height of the tree, in order to balance this is unbalanced binary search tree. This is the balanced binary search tree. To balance the unbalanced binary search tree, we go for AVL trees. Thus, AVL tree we can define as an balanced binary search tree. That means balanced binary search tree in which every nodes balance factor, every node balance factor is either 0 or -1 or +1. Okay, that means now I added one more thing. So we know that what do you mean by balanced binary search tree? Balanced binary search tree means binary search tree only. That means both the left subtree and right subtree should be balanced. Okay, so that is we know. So now that, but in the balanced binary search tree, every node balance factor should be either 0 or -1 or +1. Now, what is you mean by this balance factor? Balance factor is equal to, now this is the formula you should know. Okay, balance factor is equal to height of left subtree of a node minus height of right subtree. That's it. Okay, so balance factor is equal to height of left subtree minus height of right subtree. Now let us take simply randomly some examples. For example, say this is A, this is B, this is C. Okay, this is one, again, binary search tree. Okay, now I want to find the balance factor of this node. Now, its left subtree is how many nodes are it having left subtree? 0 nodes. Minus how many nodes it is having right subtree? No, 0. So 0 minus 0 is equal to what? 0. That means balance factor of this node is what? 0. The balance factor of this node is what? 0. Similarly, now check what is the balance factor of this node. Balance factor of this node is equal to what? Height of left subtree. Height of its left subtree is what? Only one node is there. Only one edge, one. Okay. Now, one more thing. So, whenever you are counting finding the height of the subtree, which are left subtree or right subtree, don't count the vertices or nodes, count the edges. Okay. This one you should keep it in the mind. So, always count what? Edges. Don't count vertices or the nodes. Now, this is my node for which I want to find out the balance factor. Height of its left subtree. So only one edge. So 1 minus. How many nodes are there in this right subtree? 0. So 1 minus 0 is equal to 1. Balance factor of this node is 1. Similarly, now what is the balance factor of this node? So this node left subtree, now it is having no. So this is complete left subtree, 1 edge, 2 edge. So height of its left subtree is 2. Height of left subtree of this node is 2. 1, 2. How many edges are there here? No. So 2 minus 0 is equal to 2. So that means balance factor of this node is 2, balance factor of this node is 1, balance factor of this node is 0, balance factor of this one node is 2. So that means, now I said what? In any binary search tree, in any balanced binary search tree, if a node, no, all the nodes should have only balance factor, only this value, plus 1 or minus 1 or 0. But I am having here my 2. So I am having here 2 I am having. So 2 means this node is not balanced node. This node is not balanced. I need to balance this. So this is not balanced. Or I can say this is one imbalanced binary search tree. Hence this is not an AVL tree. Because AVL tree is a balanced binary search tree. This is not balanced. Now let us take one more example. Okay, now again, come. First we need to find the balance factor. Now let us take balance factor of this node. Now it is having how many nodes in the left subtree? 0. Here 0. So 0 minus 0, 0. Again for this one. Okay, no nodes in the left subtree, no nodes in the right subtree. So 0 minus 0, 0. It is having how many? 1 edge here, 1 edge here, 1 minus 1, again 0. So this is my balanced binary search tree. So hence this is my AVL tree. This is not the AVL tree. So hope you people understood what do you mean by balanced binary search tree and what do you mean by imbalanced, or some people use the word unbalanced. Okay, unbalanced binary search tree or imbalanced binary search tree. When we call binary search tree as unbalanced or imbalanced, if any node balance factor is other than these three values, then that is an unbalanced or imbalanced. Now to make this imbalanced binary search tree to balanced binary search tree, that means to convert into AVL trees, we are using some transformations. That means I need to transform this into another form. Okay, instead of this in this fashion, I have to transform in some other form. How to transform? Using 4 different types of rotations. Okay, that we are going to discuss one by one now. So before discussing 4 different types of rotations, we need to remember few points, especially 3 points we need to remember whenever we are doing any type of rotation. What are those? The first and foremost thing is always we need to apply rotation only among 3 nodes only among 3 nodes only, not more than 3 nodes. Sometimes we 2 nodes also, but maximum only on 3 nodes. Maximum, at the case of maximum. Minimum 2 nodes also are possible. Okay, but not more than 3 nodes. I'll repeat. Okay, whenever we are doing any type of rotation, we need to apply rotation only among maximum of 3 nodes, not more than 3 nodes. That's the first point we have to remember. Second point is again very simple. In any binary search tree or in any AVL trees, there is no duplicate elements or repeated elements, no duplicate or repeated values or elements or keys, whatever you can call. That means no 2 values should be same. All the values should be distinct, unique. Okay, that is the second point. The third point is sometimes what happen in my imbalanced binary search tree, more than one node balance factor is other than 0, minus 1, plus 1. Okay, if more than one node is not balanced, more than one node is balanced, now which node we have to balance? That is the question. So from the leaf node we need to calculate. From the leaf node you keep moving towards the root node. Whenever you find the first ancestor imbalanced node, okay, that we need to balance. Okay, always balance. Which one? Always balance the first ancestor imbalanced node. Okay, these are the 3 points. Okay, if you not understood all these 3 right now, not to worry. I will go through the examples. Okay, I will do for this topic, I will do two examples, how to construct AVL trees. Very important for the exam point of view. So I will do two problems, then you can understand. But as of now, I hope this second point is very, very clear. There is no repeated or duplicate or redundant element in our tree. Okay, so now let us see the four different type of rotations one by one. So let us see the case 1. Case 1. Assume my elements are like this, say 5, 3, 1. Assume this is my binary search tree. Now first of all, first calculate the balance factor. Let us see whether it is balanced or imbalanced. Okay. Now calculate the balance factor of this one. How to calculate? Left subtree, height of left subtree minus height of right subtree. There is no node here. So 0 minus 0, 0. For this one, height of its left subtree is one edge is there here, one edge minus 0. So 1 minus 0 is 1. Okay, this is 1. Balance factor of this node is 1. Now for this one, you count here. Left subtree. This is the left subtree of this one. 2 edges. So 2 minus, here there is no 0 is equal to 2. That means this node is what? Unbalanced or imbalanced. Now I need to make this as imbalanced. Now first of all, why this node becomes imbalanced? After 5, I inserted 3 here, and then that means here element came in this order: 5, 3, 1. So first 5 I inserted, then I 3 inserted at the left of this 5, and then again left of 3 again is left. That means here the imbalance occur because of left of left. This is the left of this one, and this is left of left. See, this was left. Okay, so now you understood clear. Okay, see, now it is see left then left. So left of left I inserted. So that means here more weight on the left side. There is no weight on the right side. So what I will do, I will make this rotate like this. See, I will rotate like this. So that means I am doing rotation towards its right. I will rotate there right. So to compensate, so here I will do right rotation. If you do right rotation, that means this is my balance factor. So this one I will bring this one. This will come up. So now it will look like this now. 3, 5, and this is 1. Now this is my balanced search tree, balanced binary search tree. See, this was, initially like this was there. Now I will bring like this. If you take any one thread, so if you pull like this, now obviously it will come up. So that's what I did now. Okay, now like this I did. So this will come up, this will come here. So now check the balance factor of this one, balance factor of here. So always one thing very simple, leaf node balance factor is 0. This is leaf node, because 0, 0, 0 minus 0, 0, 0, 0, 0 minus 0. Now this node balance factor, it is on one edge. One edge here, 1 minus 1, 0. So all the nodes balance factor is 0 only. So this is my balanced binary search tree, and this is my AVL tree. This is not the AVL tree because balanced factor of this node is 2. This is the imbalanced node. Now this imbalanced node we made it as balanced. So this is what right rotation, that's the case 1. Okay, now let us see case 2. Case 2 is simple. Again, the same thing, instead of taking on the left, now take in the right like this. Okay, now let us say case 2. Assume instead of this, assume I got the element like this. Now this is the given elements. For this I need to construct what? Binary search tree. Now, 1. First I constructed 1 here. Then next what? Then next element 3. Now 3 is greater than this or lesser than. If it is lesser, I have to insert at the left. Since 3 is greater than 1, so I am inserting at the right. So again 5, greater than the 1, come to right side, greater than the 3, come to here 5. Now this is my binary search tree. Now let us see whether it is balanced or imbalanced. Now again calculate the balance factor of this one. There is no left subtree, no right subtree. So 0 minus 0, 0. Now for this, there is no left subtree, but there is a right subtree. 0, here 1, 0 minus 1. 0 minus 1 is equal to minus 1. Okay, now calculate the balance factor of this one. Here there is no 0. 0 minus, here 2. 1, 2 edges are there. 0 minus 2, how much? Minus 2. That means again this node is what? Imbalanced node, because its balance factor is not 0, not minus 1 or not plus 1, other than this, that is minus 2. So this is imbalanced. So it is not an AVL tree. Now why this node becomes imbalanced? To this node I have inserted towards right, then again right. That means more load on the right, there is no load on the left. So I inserted right of right. So that is the problem. So that means here I inserted right of right, right of right. Okay. So to balance the load both the side equally, now what I have to do? There is no weight or no load on the left. Now I will pull like this left rotation. So that means now I will rotate here like this. That means now here, see here, in this example I rotate towards right, right. Now I make it towards left. To compensate right of right, this one, I turning towards its left. So this is what the left rotation. So left rotation I am doing now. So if you do left rotation, what happens? See, now this thread I am pulling like this. Pulling like this means this will come up, this will come down. So now here it becomes 3 and here this becomes 1 and this becomes 5. Now again the same thing. Now balance factor of this is again 0, 0, 0. Now this is my balanced binary research tree, hence it is an AVL tree. So this is the two cases. So it's straightforward. And in both the cases, we did only single rotation. Okay, but there are some situations, suppose the same elements if come in another order, not in descending order like this or not in ascending order like this, if it comes in some another order, sometimes we may do double rotations. Let us see those double rotations. Okay. Now I go for what? Case 3. Suppose instead of that, suppose my elements are arrived in this way. 5, 1, 3 random. See, not like descending order like this or not ascending order like this. Now what happens? Now first element is 5. So I did this 5 inserted. Now next element is 1. 1 is what? Lesser than the root element. So where I have to insert, left or right? Yes, towards right, because lesser element should be at the left. So here I am inserting 1. Now next element is 3. 3 again is lesser than what? Root node. I have to come here. But compared to this one, suppose the 3 element is lesser than this one, again left. But it is not case, it is greater than that. So I am going to here 3. Now this is in this case. Now in this case, it is not. Now again, count first to check the balance factor of every node. Now, so for this, I will write it properly. Once again, the same thing. I will rewrite 5, 1, 3. Now balance factor of this node 0 minus 0 is 0. Here there is no 0 edges. Here 1 edge. 0 minus 1 minus 1. This also fine. Now here for this left subtree, this is entire left subtree. This is left subtree. There is no right subtree. Okay, 1, 2 edges. Okay, 1, 2 edges are there here. 2 edges are there. 1, 2. So this is 2 minus 0. 2 minus 0, 2. Again, this is my imbalanced node. This is my imbalanced node. Again, I have to do balance. So now, how to do this balance? Now, first I cannot make directly here like these two. Okay. Now, why this happens here? Why I did only single rotation? Left, left, left of left, right of right. But now here what I did? First I inserted at left, then I inserted right. So that means I did here right of left. Right of left. This is left, this is right. Right of left rotation. So to compensate for left, I have to do right. To compensate right, I have to do left. So I have to do LR rotations. So that means now I have to do what? LR rotation. This is a double rotation. So how LR rotation? First you need to apply here. First you apply here. First apply here. Now what I will do, first here what I will do, here you make first what? Left rotation. So this is left rotation. You rotate like this, first left rotation. If you do left rotation, okay, see first left rotation, what happens? This is 5 as it is. Now if I do left rotation, this is there. Now like 3 will come here, 1 goes down. 3, 1. This is 5. This will happen. See now, see, once I did rotation like this, now it will come like this. Okay, this 3 will come, 1 down. This is what. Okay. Now again calculate the balance factor of this one. Leaf node 0, 1, minus 0, 1, 1, 2, 2 minus 0, 2. Again, mind this node is imbalanced node. Now again here what? Left to left. So you do right. Now what I will do? Here I will do what? Right rotation. So if I do a right rotation again here. So then what I got is 5. See right rotation, same in this case. Okay. So 5 here, okay, not 5 here. 3 goes in this position, 5 come here, and 1 goes here. This is what? Balance. So that means directly I can say I did here what? Left first and then double rotation, left right rotation. Or you can do directly also you can do. How directly? So I will show you. So 5, 1. So you can think this as a formula. If this is the case, you just what you do, this one you replace with this one. This node you replace, this will be remain as it is. This node you replace this one, and this one you bring it to down. Okay, so this will leads to like this again. So this will comes here 3. This will be as it is, and this will comes here. Same thing I got. Okay, this is case 3. Now exactly ulta I will get another one. So I will clean it the another for that one. So now the last case. Now if you the elements arrive in this fashion. Now first element is 1. Now second element is 5 greater than, so 5, check with the root node, 5 greater. So I have to insert at the what? To the right. Then next element is 3. 3 first check with the root, greater, come to the right, lesser, now come to the left of the right. Now check the balance factor again. Now root leaf node, no node here, no edges, 0 left subtree, right, 0 right subtree, 0 minus 0, 0. Now 1 edge here, 0 edge here, 1 minus 0, 1, and here left subtree there is nothing, but here 1, 2 edge, 2, 0, minus 2, this is 2 minus 2. So this node is again imbalanced. Again here we got imbalanced because first I inserted the right, then I get left. That means this is because of right left insertion. So that means right of left. So you balance it by doing what? Ulta. Okay, that is left of right. Okay, now for that what I have to do? Now again apply rotation here first. Okay, so this is not R, sorry, this is left of right. So this is left of R. So to balance it, first what I will do, so this one I will rotate towards its right for this one. Okay, R, right rotation first. If you do right rotation, what happens? Only on these two nodes. That's why I marked in the red. Okay. Now if I do like this, now I'll get 1 will be as it is. Now when I did this one, right like this, now it did like this. This one comes here, this one comes here. Okay, so this is 5 and this is what? So when I shift this one, when I shift like this one, so like this one, this 3 comes here, 5 goes here, and this 3 will come here, this will be the 5. Okay, now Again, check the balance factor. Leaf node 0 minus 0, 0, 0 minus 1, minus 1, 0, 1, 2, 0 minus 2, minus 2. Again, this is my imbalanced node. So again, to make it balanced, again here, too much load on right. So what to do? Move towards its what? Left. That first I did R, then I did left. Okay, so that means now if you move like this one, so here I did what? Left rotation. So 3 comes here, 1 comes here, 5 goes here. This is my balance tree. That means to this only I did first what? Right rotation, left rotation. So we discussed 4 different type of rotation. One is right rotation, left rotation, and the case 3 left right rotation, and last one is right left rotation. So 4 different of rotations. So first 2 are single rotation, the last 2 are double rotation. Hope now you people understood this one. That means in all the cases we put rotation policies only among maximum on 3 nodes, and we did on 3 nodes, 2 nodes also here. In the case 1, case 2 we did on 3 nodes and 3 nodes, but here we did on 2 nodes also. That means maximum among 3 nodes. Now hope these 2 points are clear. Now for some examples what happened here, either always we never get imbalanced node at the leaf nodes. Either we will get at the first level, second level, that means in the intermediate level only we will get. Suppose we are not getting the imbalanced node at the leaf node, and we are not getting the last but one node or level also, but there if we get, that means in the big trees, in the between, if we get any imbalanced node, so we will get more than 3 nodes, 4 nodes. At that time, how to apply? For that, we need to apply this rule. Okay. For that, let us take this example. Suppose this is the case. We are having 3 nodes, and this node is having its left subtree. So this is again whatever the height, whatever the number of nodes, whatever the height of this one. Okay, assume more number of nodes are there under the left subtree. So this is the left subtree of this B left subtree. Similarly, this C has having also some nodes, but lesser than this one. C left subtree, C right subtree. Similarly, this is A's right subtree. Suppose in this case, what we do? So in this case, now simply what I have to do, you replace this one. Okay, assume this is my unbalanced. Okay, this level. You move this one to here. Okay, if you move this one, now here, this one will come here. So this one I'm moving here means what I'm doing, I'm towards this left rotation, and I'm moving this one is right rotation. Okay, so this is move you towards this one, and this is your this one, left and right rotation. If you do like this, what happens? Okay, now same thing with right. Not A. Okay, so when you move this one, this C will comes here. This will be as it is. And this A will go here. Now, A right subtree is what? A right subtree remains A right subtree only. This is A right subtree only. This will remain as it is, and B left subtree remains also same. This is B left subtree. Now this C left subtree, this is lesser than C. C lesser than C means lesser than C should be where? Towards this left subtree only, but I am having only space here, so I have to keep here. Now this is yours C left subtree. This C left subtree comes to the left of the C only. So here on the space, here I'm having. Okay. Next, this C right subtree means greater than C. Greater than C means you should come right, and right I'm having here only the option. So it should be come here only. So this is your C's right subtree. Okay. So this is the formula. You can consider as a formula or method, whatever. Okay, so hope you understand this special case also. The four cases, 2 single rotation, 2 double rotation, that is left rotation, right rotation, left right rotation, right left rotation, and this is a special case. If you understood some 50% also fine. Okay, so now I'll take 2 examples. I'll take first example. Okay, so now go to that example. Assume in the exam you will be given some set of elements. This is a set of elements. For this you need to construct AVL trees. Now I am explaining how to construct the AVL trees for the given sequence of number. Assume this is the given sequence of number in the exam. First number is 5. So 5 simple over first step. Okay. Now this number is done. This number is done. Next number is what? 6. Now 6, compare with the root node. 6 is lesser than or greater. If it is lesser, insert at the left. Since 6 is greater than, where to insert? To the right. So I inserted at the right. Okay, I'll write a separate step. Okay. So 5, 6 towards right. Okay. Second step is also done. Now, next 8. Where to insert? Again, check with the root node 5, and then 8 is greater than 5. Then come to the right, greater than. So insert here. So 5, 6, 8. So my third element is also done. Now check 3. Now again, fine. So whenever you keep inserting, you need to check its balance factor. Now check. So there is no node 0 minus 0, 0. 0 minus 1 minus 1. This is 0. This is leaf node 0. Now 0 minus 1 edge. 0 minus 1 minus 1. 0, 1, 2, 0 minus 2 minus 2. That means now this is my node which is imbalanced. This is imbalanced. Why? Because left of left. So what to do? Since left of left, you make it what? Left of left means, so compensate this, reverse this. So that means you have to move towards its left. Sorry, right of right. Right of right. So I have to move left rotation. So if you do left rotation, so left rotation, if you do that one, what I got? So since this one I am taking like this one means this thread I am pulling. So if I am pulling like this, it will come this one. 6 goes upper. Okay, 6 go upper. 5 comes here. 8 goes here. See, still it holds the property of binary search tree. All the elements left subtree are lesser than the root node. All the elements in the right subtree greater than this one. So balance factor of this one is again leaf node 0, 0. 1 edge, 1 minus 1, 0. Perfectly balanced. Okay. So this is done. Okay. Now to this, see, I'm coming in this direction. First, second, third, and this I transform by doing left rotation. Now to this, now I have to insert what? Next element is 3. So now where to insert here? 3. Check with the root element. 3 greater than, lesser than 6 or greater than 6, lesser than 6, come to the left. Check with this one. 5, 3 is lesser than, so come to this one. Now I am writing here. Okay, so this is my 6, 5, 8, so 3 to the left of this one. Now again, check its balance factor. Leaf node 0, 1, minus 0, 1, 1, 2 edge, 2 minus 1, 1, this is 1, so this is root node 0, perfectly balanced. Okay, all the node balance factor is either 0 or 1, no. Okay, fine. So now this element is also done for me. Now check for the next element 2. Now I'll rewrite for this one again. I'll rewrite this one, the same thing I'll rewrite. 6, 5, 3, 8. Now check. Next element 2. Lesser than, come here, lesser than, come here, lesser than. So I'm inserting 2 here now. Okay. So now again calculate the balance factor for this one. Leaf node 0, leaf node 0. Check this one. For this one, left side tree height is 1. This is 0. 1 minus 0, 1. Now for this one, 2 edges 1, 2, 0, 2 minus 0, 2. Now check 1, 2, 3. Minus 1, 2. Now this is the first example we got in which 2 nodes are imbalanced. This is what the thing. Now 2 nodes are imbalanced. Which one to do balance? First one. So come from the leaf node. So when you're moving towards its root, whichever you got the first imbalanced node, that is what to do. That's what the meaning. So always balance the first ancestor imbalance. So this is the ancestor node of this node. Okay, this is parent, grandparent, ancestor. Okay, now this is the first ancestor, this is second ancestor. And I'm moving from here. So now I need to do rotations on this 3. That was the first sentence. We need to do, so we now cannot apply on the 4 nodes. We need to apply maximum on 3 nodes. Now I have to apply only maximum on 3 nodes. Now, why I got this node is imbalanced? Because I did left, 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 left of left. So to compensate, what I have to do? I have to do right. So if I do right here. So now I will do here, right. So now what happens? Now instead of this one, if you should slightly tilt. So this 2 comes here, 3 goes here, 5 comes here. So now the resultant is 6, not 6, 5, okay. 6 will be remain as it is, 8 as it is. Now here I will get 3, and here I will get 5, and here I will get 2. So instead of this one, this 5 comes here, 3 goes here. That's what I did. Now calculate the balance factor of equilibrium node. Leaf node 0, 0, 0. This one 1 edge, 1 edge, 1 minus 1, 0. 1, 2 edge, 1, 2 minus 1, 1. Perfectly balanced. Now the 2, this is also inserted. Now 2 also inserted. Next check with the 4. Check with the 4. Now I will rewrite this again. I will rewrite the same thing again. 6, 3, 8, 2, 5. See, again it holds the property of binary search tree. All these elements are lesser than the root node. All these elements are greater than this one. Okay, lesser one side, greater one side. Now, to this now I need to add what? 4. I have to insert 4. Wait, check with the root node. 4. Lesser than this 6 comes to left. 4. It is greater than this. So go to here. So now this 4 is lesser than this. Now I come to the left one, added here. Now again calculate the balance factor of this one. See, root node 0, 0, root node 0. Always leaf node. Leaf node balance factor is always 0. Now check this one. Now left subtree 1, 0, 1 minus 0, 1. Here 1, 1, 2. Right subtree 1, 2. 1 minus 2, minus 1. Next, 1, 2. This is the left subtree always find the longest path. So this is my longest. 1, 2, 3. 1 edge, 2 edge, 3 edge. Minus 1. 3 minus 1 how much? 2. Again, this is what? Imbalanced. So this node is imbalanced. Now I told apply the formula. The last special case what I explained, that case. Now what I did, you move this node here. You move this node here. If you move this node will come to this one. Now with that, so that means first I am doing this one. So that means I am doing first like this means left, and then doing like this left right rotation. So according to the formula, so this 5 goes here. 5 goes here, 6 comes here. Okay, this 3 will remain as it is. Okay, now 8 is the right subtree of 6, it remains as it is. Its left subtree remains as it is. Now this variable will go 4. 4 is left of 5, so it should be on the left of 5, but left of 5 I am having here only the option. So this is my 4. See, now you calculate the what? Balance factor. Leaf node 0, 0, 0, 1 edge, 1 minus 1, 0, 1, 2, 2 minus 2, 0. Here for this, there is no left subtree, here only one left subtree, so minus 1. Okay, perfectly balanced. Now again, all these elements are lesser than this, all these elements are greater than this. Holds the property. Now, this element also we inserted. Now the last element I need to insert for this. Again, I will rewrite this again for you. 5, 3, 6, 8, now last element is 7. Now check with the element greater, comes to right, greater, comes to this one, lesser. So I am inserting left of this 8. Now calculate the balance factor. Leaf node 0, 0, 0. Now this one. 1 minus 1, 0. Now 1, 2. Here 1, 2, 3. 2 minus 3 minus 1. This one. For this one 1, 2. left, right side tree, 0, 0 minus 2, minus 2. Here 1 minus 0, 1. So all the nodes are balanced except this node. Now what I have to do? So now again you have to double rotation. So first you apply double rotation. So first here, okay. Now first I am applying here. Okay, first I am applying here. So that means now I am doing here first right rotation. This fourth is RL rotation. First this is right rotation I am doing, right rotation. If I do this right rotation, I got like this 5, 3, 6. Now if I do right rotation, so it will go like this. 7 comes here, 8 goes here. 7, 8. Okay. Now this remains as it is 3, 2 and 4. Okay, 2 and 4. Now again, if you calculate here, again, this is the leaf node 0, 0. This is minus 1. This is minus 2. This is 0, 1, 2, 3. This is minus 1. Again, this node is imbalanced. Now again, you need to apply what? Left rotation here. So that is RL, as already I told you. Okay, this is left rotation. If you do left rotation, this one, so 7 comes here, 6 goes here, 8 comes here. This one, the second case, what case 2 we have what we discussed. Okay, so now I will write here. Okay, I will write here. So 5, 3, 6 will be as it is. No, so here this will comes here. 7, 5, 3, 7, 6 comes here, 8 comes here, and this will remain as it is. 2, 4. This is perfectly balanced. You check the balance factor. This is the leaf nodes. All these are 0, 0, 0. This is also 0, 1, 2, 2, 2, 0. Perfectly balanced. So this is my left side tree. All are lesser than. This is right side tree. All are greater. Both the sides are balanced. So this is my what? AVL trees. Now you can ask the question. What is the use of doing all these things rotations? See, first again, first, second, third, get it applied left rotation, then comes the fourth one. So then here I got the imbalance. So here I did right rotation, then here the formula I use, the double rotation, again double rotation. Okay, so like this it comes. Okay, so this is the final answer for this problem. Okay, now the same element I will take, same element. Suppose, for example, assume, hope it is understood. Now let us say, assume I want to search the key element I want to search is, say, for example, 4. Check without elements, not matches. Now 4 lesser than, come here, not matches. Now 4 is greater than 3, comes here, greater than, so matches. So 1 comparison, 2 comparison, 3 comparisons. I found the key element at the 3 comparisons. So height of this is also 1, 2, 3. But assume this will come in the ascending order itself. That means the same element, if I got the same element, it's a 2, 3, 4, 5, 6, 7, 8. Suppose the elements are this ascending order itself. Now its tree will be 2, then 3, then 4, then 5, then 6, then 7, then 8. So like this it goes. Okay. Now instead of 4, let us take, see, let us take 3, only 3 comparisons. Suppose 4, here also 3 comparisons. First matches, match, not matches, matches. 3 comparisons at the origin. But let us take here 8. Suppose your key element is 8. Key element is 8. Not matches. Then 8 is greater than, comes here, not matches, matches. Again 3 comparisons for 8 also. But for 8, so not matches, not matches, not matches, matches. So how many? 7 elements. That means to set the key element in the, on any case, successful or unsuccessful, maximum of 3 cases the height is 3. But here 7 comparisons, 3 comparisons, 7 comparisons. So this is the beauty of AVL trees. If we go for AVL trees, we can search the element faster. This is the beauty of this AVL trees. Hope you people understood. Okay. If anybody understood, fine. If anybody not understood or having some doubt, now for them I am solving another example. It will take maximum 5 minutes, so you can watch that one. Let us take, this is the sequence of number given. For this elements, I need to construct AVL trees. First element 8, so that will be the root. That's it. Next 12. So 12 is greater than this 8, so it should come towards the right. I will attach it as a right child. Fine. So both now balance factor is 0, balance factor is 0. Here 0 minus 1 balance factor. So perfectly balanced, not a problem. So next element is 20. So 8, 12 already is there. Now 20. So okay, this element is done. This element is done. 20. It is greater than 8. Come to the right. Greater than 12. So come to the right. I am inserting it right. 20. Now calculate the balance factor. Leaf node 0. 0 minus 1, 0 minus 2, that is minus 2. So it is imbalanced. This node is imbalanced. So what to do? This is right of right. So make towards left rotation. If you do left rotation, what I got? So if I do like this, now if I do like this, 12 comes here, 8 goes here, 20 comes up. So for that, I am saying this is 12, this is 8, and this is 20. Okay, so this is done. Next, now if you check the balance factor, 0, 0, 0. Now this element is also done. Next, to this I have to insert 15. So now 15, so I'll rewrite again. So 12, 8, 20, 15. Greater than this, come here. Lesser than this, so I'm attaching here 15. Next, now check the balance factor. Leaf node balance factor always 0. This is 1 minus 0, 1, 1, 1, 2, 1, 2. So 1 minus 2 minus 1, perfectly balanced. Now to this, now that means 15 is also done. So rewrite this once again. 12, 8, 20. Now to this one, 19. Now greater than the root, come towards right. Lesser than, come here. Greater than, so 19 comes here. Now check the balance factor for this. 0, leaf node 0. Next, there is no edge. One edge, 0 minus 1, minus 1. Here 2, here 0, 2 minus 0, 2. So here 1, 2, 3. Right side 3, here 1, 1 minus 3, minus 2. Again, I am having two nodes are imbalanced. But first one is what? This is the first answer come to from the leaf node. So coming from the leaf node, this is the first ancestor node which got imbalanced. So I am applying only here. I am applying here. Okay, first what I will do, so here left right combination, directly I will write now left right, left right. That means first you do your left, first left, then after that if you left do this, 19 comes here, 15 goes here, then you do what? Right. Okay, so I got, now what you do, replace this one. If you have confusion, I will say one more method. See, now you apply only this, you write separately. Write separately 20 and then 15 and then 19. One more shortcut. Okay. Now I am applying what here? I am left right means now this becomes 20. This will go like this. So 19, 15. Okay, now you do this one. If you do like this, 19, 20, 15, that you replace here. That's it. Now if you do like this, so 12, so this left side 8, this is 19, and 19, this is 15, and this is 20. So just write only this part separately. I did one left and then right. That's what result. This I am replacing in this place. That's it. Now you check the balance factor. Leaf nodes 0, 0, 1 minus 1, 0, 1, here 2, 1 minus 2, minus 1. Perfectly balanced. So now this 19 also inserted. Next 16. So now rewrite 12, 8, 19, 15, 20. Now to the 16. Greater than this one, come right one. Lesser than this one, come left side. 16 is greater than this one. So greater than, I am going for here. Now check the balance factor. Leaf node 0, 0 edge, 1 edge, 0 minus 1, 1. 2 minus 1, 1. Here 1, 2, 3. 1 minus 3, minus 2. Now I got here. So again, the formula, special case. Now you replace this with what? This one, that is right first. And then, so this one what? Okay, this one you should here. Okay, not here, here. So this is towards the, like this. That is right, this is left. Okay, now if you replace like this, now this will goes here 15, 15, and this 19 remain as it is, 19 remain as it is, and its right subtree will remain as it is 20. Now this will go, and then this will come this side 12, and its left subtree remains as it is. Now this one right of 15, so right side here, here only the space. This is 16. Okay, now check the balance factor. 0, 0, 0, 1 minus 1, 0. Okay, here this one 1 minus 0, 1, 2 minus 2, 0. Perfectly balanced. This is also done. The last element. Now the last element, I will rewrite again 15, 12, 19, 20, 16. Then I am having 8. Now to this I will insert 10. Root 10 lesser, come to the left, lesser, come to the left, greater. So I need to insert at here 10. Now again you check. Balance leaf node 0, 0, 0. This is 0 minus 1, minus 1. 1, 2 minus 0. This is 2. Okay, that's 1, 2, 3. 3 minus 2, 1. 1 minus 1, 0. This is imbalanced. So this is here I need to apply double rotation again. Okay, here double rotation. First again I told what I told. You write this as separately. It is separately 12, 8, 10 I written separately. So first what you apply? First you apply here left rotation first. So if you do this one, what happens? So 12, 10, 8. Now you do what? Right rotation. Now what happens? Now I got 10, 12, 8. Now this one you replaced in this place. If you replace that, I got 15. Now towards this left, this is 10, 8, 12, and this as it is. This is 16, 20. Okay. Now if you check the balance factor, 0, 0, 0, 0, 0, 0, 0. So perfectly balanced. So this is balanced binary search tree. So height balanced search tree. That's what AVL tree. Okay. So hope you people understood. If you have any questions, please write in the comments. Thank you. Thanks for watching.